Okay, so today I want to teach the analog to digital converter and digital to analog converter. This is the first lecture, introductory session of the ADC and DAC. So now, why, 1 minute. Yeah. So due to the bandwidth issue, I should off the video. So now, why we will go for the ADC and DAC? Why we will learn the ADC and DAC? So in many of the applications, the signals are not available in the digital form. So most of the physical quantities like the temperature, pressure, displacement, vibrations, etc. are available in the analog form, and we can only hear by our ear through the electrical signals, all of you know. Okay, so if we can able to hear the analog signals, electrical signal is the analog signal, so all the digital signals should be converted to this electrical signal before reaching to our ear. So then we can hear. So for this reason, this is very much important. The digital signals should be converted to the electrical signals. That means the analog signals to hear. So for this reason, the digital to analog converter is very important. But there is some advantage of the digital signals, like it is more noise immune. Okay, so digital systems manipulate the discrete elements of the information. Discrete elements are nothing but the digits, such as the 10 decimal digits, 26 letters of alphabets, and so on. Digital systems make use of physical quantities called the signals to represent the discrete elements. Okay. Another important features of the digital system is the discrete elements of the information are represented with the group of bits called the binary codes. The digital systems, like a digital computer, is a programmable device which may be programmed to perform a variety of tasks. Okay. So there is some advantages of the digital systems, like it is easy to design, reliability and the reproducibility of the results is very high. The output of the analog system varies with the variation in temperatures, power supply, voltage, component aging, several other factors also there. But this is not the case with the digital systems. The digital systems always reproduce exactly the same results with the same set of inputs and the circuit components. It is more flexible, more functionality occurs in the digital systems, and another very much important features of the digital system is it is reprogrammable. So programmability features are there in the digital systems. Speed is also very high, and the manufacturing cost of the digital system is less than the analog systems. So these are the advantage of the digital systems. The more advantage is it is noise immune, manufacturing cost is very less, it is very fast, okay, and it is more flexible to design, and it has more reliability. So for this reason, the analog systems will convert it to the digital systems. Okay, so for this reason, we should know the analog to digital converter. Okay, so now if if I come to the more features of the digital to analog converter or the analog to digital converters, that the real signals are the analog quantities varying continuously with the time. Human voice, as I already told, the human voice in ear is an analog signal. Our ear can permits only the analog signal to hear any sound which is varying continuously with time. Digital formats offer several advantages: less expensive, more reliable, easy to manipulate, flexible, and compatibility with the other digital systems, and in very much integrated in network. The size is very less of the digital systems. Before the digital era, we have a large number of radio, large size of the televisions. Okay, so now it is come to a very small size mobile phone, where we will get all the features of the radio and the televisions. Okay, so the digital formats are mainly used in digital signal processing, storage to store the data, computers, robust transmission of the information. Digital to analog and the analog to digital converters constitute and the essential link when the digital devices interface with the analog devices and vice versa. So the analog device can convert it with the help of the analog to digital converters to the digital systems and vice versa. Okay, so they are important building blocks of any digital system, including both the communication and the non-communication systems, besides having their applications. So these are the functional block of a general ADC and DAC systems. This is the physical variable. The transducers can convert one signal to the another signal. This is the n-bit ADC, analog to digital converter, produces the digital signals. Then it will as the input of the digital system. Then by the digital to analog converter, these digital signals will be converted to the analog signal. Then there is an actuator which can amplify or same shape or same type of the signals, and then we will get the desired physical variables. Okay, so this is the main building blocks of a communication and non-communication systems. So now come to the some parameters of the DA converter or the AD converter. So first come to the DA converter. So the DA converter is important not only because of its needed at the output of the most digital systems, where it converts a digital signal into analog voltage or current. Not only the voltage, it should convert in the current also, so that it can be fed to a chart recorder, for instance, for measurement purposes, or a servo motor. The digital servo motors are also there, which can control by a pulse. Pulse means a digital signal. Okay, motor in a control application. It is also important because it forms an indispensable part of the majority of the AD converter types. The AD converter too has the numerous applications. When it comes to the transmitting analog data, it forms an essential interface with a digital communication system, because we know all of the now the communication medium is the digital medium, the mobile phones, where we use the CDMA, okay, code division multiple access, okay, and also the GSM networks. So there is also the digital format of the communication system. You should know in the 5th semester analog and digital communication. So system where the analog signal to be transmitted in digitized at the sending end with the AD converter. It is invariably used in all digital readout test and the measuring equipment. Whether it is a digital multimeter or a digital storage oscilloscope or even a pH meter, the AD converter is an important and essential component of all of them. Now come to the specifications of the digital to analog converter. First, What is the first parameters of the specification of a digital to analog converter? That is the resolution. This is the very important parameters of a DAC. Okay. So when we choose any DAC, we should first consider the resolution. What is called the resolution? The resolution of a DAC is the smallest change in the output of the DAC for any change in the digital input, such that the change of the output with respect to the change of the input is called the resolution. How it will be measured? It will be measured as like this. Percentage of resolution means the step size by the full scale output. Full scale output means, suppose this is a 15 volt operated DAC. Okay. So full scale is the 15 volt. Okay. So what is the step size? Step size means this is the 1 volt, 0 volt to 1 volt. When suppose this is a, if I make it like this, okay. So what is called the step size? Step size means if I put the curve like this, like this, then this is called the step size. Okay, this is called the step size. If I go through a numerical problem, then it will be very much understandable to you. So now the mathematical calculation of this, the step size, what is the value of the step size? Here the value of the step size is 1 volt. Okay, so every stairs, what is the height of this stair is called the step size. For this example, here the step size is 1 volt. Clear? What is the full scale? Suppose it is a 3-bit DAC, then what is the full scale? 2 to the power 3. That means the 8 volt. Okay. So if we calculate it, then 0 to 7. So what is the full scale? Full scale will be 7 volt. Okay. Clear? No. Here this is the 16 volt. 0 to 15. So that means there is 16 steps are there. So this is a 4-bit ADC. What is the value of this? Maximum value? 1111. What is the maximum value?
Sir, 15, sir.
15. So for this reason, this is the full scale. The maximum value of the bit, decimal value, this is called the full scale. If it is 3-bit DAC, then what will be the full scale?
7, sir.
7. Clear? And step size should be mentioned in the example or the problem. So
Sir,
if there is any 1 volt step size, then how many steps will be there in the 15 volt? 16.
16 steps.
Okay, so 0 to 15. So this is what will be the step size. How many stairs are there? 15. This is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Clear? So full scale value means the number of stairs also. Okay. So now come to the next point. In other way, the resolution is the number of steps, which I already told. The number of steps into which the full scale output is divided. If a 4-bit DAC can resolve the FSO up to 15 levels, then each level of the output is called the step size, and for the higher number of the bits of the resolution will be better. Whose resolution is high, this type of DAC or ADC will be very much appropriate. Okay. So percentage of resolution in the other form is 1 by 2 to the power of n minus 1 into 100. That means this is the step size 1 volt. This is the full scale. Full scale means 2 to the power of n minus 1. For 4 bit, it is 2 to the power of 4 minus 1. That means 15. This is the 15. If it is 3, then 2 to the power of 3 minus 1. That means 7. So full scale is 2 to the power of n minus 1. Step size is 1 volt, which is defined in the problem. Normally, the resolution will be in millivolt. This is very much important for the MCQ. And in the gate examinations, one example, one problem should be there from the resolution calculation. So it is very much important for the gate. There is two types of formula is there. One is this percentage of resolution is equal to step size by full scale output into 100. Another is this. Okay. Now,
hello sir,
Hello?
step size টা কি
please loudly.
তো স্টেপ সাইজটা কি সবসময় 1 ভোল্টই হবে না
No,
প্রবলেমে
this
দেওয়া
should
থাকবে?
be mentioned. This should be mentioned in the problem.
Okay.
If there is no mention, then you should consider as 1 volt. In general, it should be in 1. Okay. If it is not mentioned in the problem, then it should be considered as 1 volt.
তাহলে স্যার এই প্রবলেমটা নিচে 2 টু দি পাওয়ার n - 1 তাহলে উপরে 1 ভোল্ট কেন হলো?
No, 2 to the power of n means this is the number of bits. N is the
Yes, sir.
number of bits. How many bits ADC is there or DAC is there?
বাট
If it is
উপরে স্যার নিউমারেটরে 1 কেন হলো তাহলে স্যার নিউমারেটরে তো স্যার স্টেপ নাম্বারটা 1 আছে তাই জন্য
No. If it is the total full scale, na. So if it is 4 bit, what will be the value?
15 sir
4 - 1 15
Yes, 2 to the power of 4 minus 1. That means 15.
আর নিউমারেটরে স্যার নিউমারেটরে 1 হওয়ার জন্য স্টেপ সাইজ 1 তাই
1 minute. Now, I should increase the volume.
আগের স্লাইডটায় তো বলা আছে আগের স্লাইডটায়
হ্যাঁ বলো।
আগের স্লাইডটা দেখেন একটু আগের স্লাইডটায় তো ওরকমই ছিল মানে
না, আগের স্টেটে ছিল ফুল স্কেল আউটপুট।
ফুল স্কেল আউটপুট মানে তো ওটা 2 টু দি পাওয়ার
n minus 1. What is the full scale here?
স্টেপ সাইজ
What is the full scale?
ফুল স্কেল 2 টু দি পাওয়ার
15 নিতে হচ্ছে
15
15. That means 2 to the power of n minus 1.
yes sir
Okay. So
sir
here it is the step size.
yes
Step size means this. What is the height of a stair? This is the step size. In general, it should be 1. Otherwise, if it is mentioned in the numerical problems that what is the step size, then you should put it here.
okay sir
Okay. So now, for consider one example. Determine the resolution of the 6-bit DAC and the 12-bit DAC. Just put the formula. 1 by 2
to the power n এর জায়গায় এক জায়গায় 6 বসাবো এক জায়গায় 12 বসাবো
6 minus 1. Then you will get it. So this formula should be important for gate. Okay. Another problem. If 6-bit DAC, that means n is equal to 6. So what is the full scale? 2 to the power of n minus 1. So that
do 6 minus 1 মানে 63
So what is the 63 steps? In the step size, দেখো এখানে বলে দেওয়া আছে step size is the 50 millivolt. Okay. So এখানে কিন্তু mention. It is already mentioned that the step size should be 50 millivolt, not 1 volt. Okay. So for this reason, the total full scale voltage should be 63 into 50 millivolt.
yes
The total number of
yes
steps into height
exactly. So steps into the height. So that means we will get the total full scale. So
Yes,
this
sir,
is
yes,
full scale. So now put the formula here. Step size by full scale into 100. So this is 50 millivolt by full scale into 100. Then you will get the result. I should arrange different types of problem for clearing your confusion. Okay, so for this reason there is two types of problems are there. One is the full scale should be calculated first using the step size, number of steps, and then you will get the resolution. And another problem is that directly you should put from the bit. And the another problem is that for
আগের স্লাইডটা একবার দেখাবেন,
বলো
লাস্ট স্লাইডটা একবার দেখাবেন একটু, এক মিনিট কোশ্চেনটা টিকে নিচ্ছি জাস্ট।
এটা
ইয়েস স্যার।
Okay, I will give you the total video and the problems, no problem. Okay, so now come to the problem 3, that is the 8-bit DAC. That means n is equal to 8. V out is there. For a digital input is there. Find the full scale output voltage and the percentage of resolution. We all of know that full scale output is equal to step size into the number of steps. Clear? So here the n is 8. So that means number of steps should be 2 to the power of 8 minus 1. And the V out is 0.05 volt. So that means the 1 bit input we will get the output is 0.05. So what will be the step size? Step size will be the V out. This is the 1 bit output. There is 8 number of bits are there. So this DAC can calculate maximum the full scale value. So maximum full scale value means for 1 bit output into the number of step size. So that is input step size is 0, output step size is 0.05.
স্যার কি বলেন এই জায়গাটা একটু বলুন না।
আবার বলছি, this is the V out. This V out means this is the 1 bit output. So that means this is the step size. Every step we put 1 bit, the DAC will convert this bit to the output voltage. So for this reason the output voltage means it can calculate every step output. So if there is number of 15 number, suppose there is a 15 number of steps are there, every output voltage is 0.05. So what will be the total output voltage? 15 into this?
Yes sir, 15 into this.
Clear? So this is the maximum output. So that means this is the maximum full scale.
Okay, বুঝেছি।
Clear? So this is the step size into the number of steps. So that is 0.05 into 2 to the power of 8 minus 1. Then you will get this. So now if you will get this full scale output, then what will be the resolution? Resolution is 1 by 2 to the power of n minus 1. So that means this into 1 by 255, that is 0.392%. So V out for an input is this. This is the wrong input. Actually input is this 0010 0010. Actually we want to calculate this. Okay, so I should correct it and I will send it to you. So if the input voltage is 00101010, then what will be the V out, maximum V out? That means this is the total output, input. So the decimal value of this is 42. Clear? 0 1 2 3 4
স্যার
5.
আগেরটা মনে হচ্ছে 0, স্যার আগেরটা ঠিকই ছিল স্যার, 00001ই হতো সম্ভবত, কেননা ওটা ইনপুট যখন 1 ছিল ওটাকে ডেসিমালে কনভার্ট করলে 1 হচ্ছে না, তো 1 ছিল 1 হলেই তো স্টেপ ভ্যালুটা বের
দেওয়া ছিল। ওকে হ্যাঁ, yes, very good, yes. So exactly, good, I am not wrong. So 00000001, because when the input is this, V out is this,
then we will get
this
step
is
value
the
from
step
here.
size is 0.05. Good, very good. But the problem should be there, that find the full scale output voltage and the percentage of resolution when the input is, the problem should be this 0 0 1 0 1 0 1 0. Then calculate what is the V out. So V out means this is the decimal value is 42. So 42 into the step size. So then 2.01 volt. So this is the full scale voltage. Okay. So this is the output when the input is this. Clear? So now go to the next problem. A certain 6-bit DAC has a full scale output is 2 milliampere. So full scale output is there. Full scale error is there. So then what is the range of the possible outputs for an input is this. So very simple. The step size will be how many number of bits are there? This is the 6-bit.
63, sir.
63. So that means 2 milliampere by 63. Then you will get the step size. So step size is this. The input is this. The decimal value of this is 32. So the ideal output should be 32 into the step size. That is the full scale. So that is the 32 into 31.7 is 1014 microampere. Error can be as much as plus minus 0.5%. Then what will be the value? That is the 10 microampere. So the actual value, actual output can deviate by this amount from the ideal value. So plus minus 1014. So that means minus 10. That means 1004 plus 10 1024. Clear? This is the error, na? This is the error means the plus minus 5%. So what will be the error of the 2 milliampere? That means 10 microampere. So this is the error. So then error means the lower value to the upper value. So the lower value will be minus 10. Upper value will be the plus 10. So minus 10 that means 1004 and plus 10 that means 1024. Because your actual value is 1014. Okay, which we will get from this, the full scale value. It may be voltage, it may be current. Okay, so it depends upon the step size, current amplifier or the voltage amplifier. Then you will get it. From the voltage amplifier, the output should be in voltage. For the current amplifier, the output should be the current. So there are so many examples are there already. Different types of examples are there. You should go through these examples. Now come to the second parameters. That is called the accuracy. The accuracy of a DAC is the difference between the output practical analog output to the ideal expected output for a given digital input. From the previous example, you have gone through the error. So if the error is much less, then the device should be more accurate. Clear? So 10 microampere is not a matter of joke. 10 microampere means a very much erroneous. It should be in nanometer form. So nano ampere or nano voltage. Micro and milli is very much important for the digital systems. So the accuracy of a DAC is the difference between the output practical analog output to the ideal expected output. You have the ideal expected output is 1014 microampere, but the error is 1004 to 1024. So this will much erroneous. The DAC is contained electronic components where the gain plays a major role. which can introduce the gain error in the output for the amplifier. For designing any amplifier, you should keep in mind that the gain plays an important role, the open loop gain and the closed loop gain for any feedback system. Due to the full scale output may differ compared to the ideal one. For an example, if a DAC of 10 volt is said to be more accuracy of 0.01%, then there will be the 1 millivolt output deviation. Then the accuracy should be output deviation by the full scale output into 100%. So put the accuracy here, then you will get the output deviation, because you should know the full scale output using the step size. So 1 millivolt output deviation. That means if this is 1 and 1 into 100%, then you will get the 1 millivolt. The another factor which implicates the accuracy is the zero offset error. For a zero input, output of the DAC reflects some offset value. It is very much important for the op-amp design. Okay, when you will design a analog to digital converters, okay, so then it will be very much important, because they are used the comparator. Comparator means a op-amp. So now the third parameter is the conversion speed. The conversion speed of the DAC is output analog value, settling time, period of a change in the digital output, digital input. This is also called the settling time period of the DAC. Normally, it will be in microsecond. This is very much important for the multiple choice questions. Okay. So conversion speed of a DAC in which range? Microsecond, millisecond, second, or the nanosecond. So it is in microsecond. But for advanced microcontroller DAC, it is in nanoseconds. Okay. And another parameter is the monotonicity. Monotonicity means it should be in monotonous. Suppose one time we use a DAC, there will be no error. After 5 minutes, when we will use this DAC, there is some 1% error, then it is not monotonic. Okay. So monotonic means if there is no error, so when we will use the DAC, it should be there is no error. So this is called the monotonicity. Okay. Another parameter is the linearity. It is as simple as the monotonicity and same as the linearity of a DAC is defined as the precision with which the digital input is converted into the analog input. Now the calculation of the linearity. If there is a monotonic step size is there in the DAC, then it should be linear. If the step size is varying in the DAC, so then it is not linear. Okay. So the linearity of a DAC is defined as the precision with which the digital input is converted into the analog output. In the ideal DAC, produces the equal increments in the analog output, that means the step size, for equal increments in the digital input as shown in the dotted line. Okay, shown in the figure. This is 0, 0, this is 0, 0, 1, this is 0, 1, 0 point, this is 0, 1, 1 point, this is 1, 0, 0 point, this is 1, 0, 1 point, like this. But due to some resistance used in the DAC for the non-linearity effects shown in the solid line. So for this reason, we will get like this waveform in the DAC by using the resistance. Okay. So now the question arises in the some interview for the DAC, the linearity, why it is shown in the dotted line and why it is like in the step size. So the answer is we use the resistance to make a DAC. Due to the nonlinearity effect of the resistance, we have this stair-like shape of the output characteristics of a DAC, but it should be in linear. Okay. So now come to the specifications of the ADC, as simple as the DAC. This is also the resolution, the same formula, but there is 1 by 2 to the power of n minus 1. Here it is 1 by only 2 to the power of n. This is the only difference. Full scale by 2 to the power of n. This is the delta Vi. That is the step size. Yeah. The resolution of an AD converter is the quantum of the input analog voltage change required to the increment its digital output from one value to the next higher code value. Suppose this is the 1/8 ADC. ADC means analog to digital. So input is the analog signal. That means 1/8 voltage, 2/8 voltage, 3/8 voltage, 4/8 voltage, like this. So this 0 is converted to 0, 0, 0. 1/8 is converted to 0, 0, 1. Why it is 1/8? Because this is a 3-bit ADC. So 3-bit ADC means 1 by 2 to the power of n. Okay. So 1 by 2 to the power of n at this point. This is 1/8. At this point, this is 2/8. And what is the value of this? Value of this, the depth of the stair is called 1 LSB. Okay, clear? For the DAC, the length of the height of the stair is called the step size. But for ADC, the depth of the stair is called the 1 LSB. Clear? So 1 LSB means, suppose one change, that is called the 0, 0, 0. So that is the 0. So then when the one stair comes, then 1 LSB will change. So that means this is 0, 0, 0. Then this should be 0, 0, 1. When the next stair will come, then the next LSB will change. So that means this is 0, 1, 0. Okay. So then when the another, that is the 0, 1, 0, the next LSB will change. Okay. Then when the another will come at this point, when the input voltage is 4/8, then what will be the value? The next LSB will come, change. Okay. So then next LSB, then next LSB, then next LSB. Here this is 1, 1. So LSB means this one. Clear to you? I repeat again. Suppose this is at 0 point, this is 0, 0, 0. When the 1/8 voltage will come, the first LSB will change. That means 0, 0, 1. Okay. When the next step size will come, then the next LSB will change. 1 will be shifted here and 0 will be changed here. Okay. So then if there is any LSB is changed 0 to 1, so then there is a scope 0 to 1, then this is 1. Another is these two are 1. So for this reason, this should be 0 and this will be 1. Again, this is 1, 0, keep intact. Next LSB will 1. Change the LSB. Okay. So then this will be changing, this will be shifted. And again, this will be changed. So one shift, one change, one shift, one change. So the ratio of the full scale input voltage ranges at the VFS to the resolution gives the minimum change of the input voltage, which can cause a change of 1 LSB at the output. Change of 1 LSB. Okay, so this can be expressed as del Vi for 1 LSB, that is the full scale voltage, by 2 to the power of n. This is very much important. What is the value of the 1 LSB? That is the delta Vi. And what is the BFS? This is the full scale input voltage. And this is the 2 to the power of n. N is the number of bits. Now, if I go for an example, that is the digital output starts at 0 for the ADC. Therefore, the maximum full scale input voltage which will cause the output to be all logic 1. All logic 1 means this 1 1 1. 1 LSB is less than the full scale output voltage. It should be less than this. This is the full scale output voltage. It should be less. Now this is 0 1 0. So then the full scale output is 0 1 0, where it is at 3 by 8. So it should be less than 3 by 8. That is the VIFS. VIFS is the maximum input voltage which can cause all ones at output.
স্যার এই জায়গাটা কি লাগবে একটু বলবেন?
আবার বলছি suppose this is the 3 means 3 designed by 2 bit 1 1. So all bits 1 set, that means 0 1 1.
Yes, sir.
তাহলে তার আগে before that it should be 0 1 0.
Yes, sir.
So until the 2 bit exists, the maximum value is 0 1 1.
Yes.
So till the 0 1 1, all the LSB should be changed like this. This is the 0 0 0. That means 2 bit is 0 0. So 2 bit is 0 0. Then next LSB is 1. Change. Then it should be less than this. Again, if it is 0 1 0 or 0 1 1, why it is not 0 1 1? Because 0 1 1 is the final full scale output for 2 bit. Okay. So for this reason, there should be one change of LSB is there. First change is 1. So the second change should be 1 0. This LSB is 0 1. Next LSB should be 1 0. Because this is already changed, na? 0 to 1 change made. So the next LSB is 1. Next LSB is 0. So this 0 should be changed at 1. By keeping the changing of the previous LSB until the maximum number will not reach.
Okay, sir.
So if it is bit by bit, na? First thing, this is the first bit, 0 and 1. When the 0 and 1 will change, then the first bit will gone. So then the second bit. So second bit should be 0 and 1. Okay. So second LSB from 0 to 1, it should be changed. Then for the second bit maximum. So second bit maximum is 1 1. Now come to the third bit. So third bit means if it is second bit is completed, then come to the third bit. That means third LSB. So third LSB is changed as 1. So now keeping intact the third bit, that means this is 1, change the first LSB. Now keeping intact of the third bit, change the first LSB and the second LSB until the maximum number of the third bit. So that is 1 1 1. Now if there is more, then it should be keeping intact of the 4 bit, then 0 0 0. Then keeping intact of the next 2 bit, it should be changed the first LSB. Then this first bit change, second bit change. Now keeping intact the third and fourth, then it should be 1 1. Then keeping intact this, like this, it will go to the 1 1 1 1. So every one bit position, the least significant bit should be changed until the maximum number will not be reached. So full scale should not be reached. Then all the logic 1 of the 1 LSB should be less than the full scale voltage. Always. For every bit. Suppose this is a 1 bit ADC. What will be the maximum value? 1. If it is 2 bit, what will be the maximum full scale? 3.
1 1.
Exactly.
Sir, 3.
So for the third bit, what will be the maximum value? 1
7.
1 1. So until the 1 1 1 will not be reached, the least significant bit will be changed repeatedly.
Okay.
Okay. So now this is the 1 IFS is the maximum input voltage which can cause all 1s in at the output. যতক্ষণ পর্যন্ত না 1 সবকটা 1 হয়ে যাচ্ছে ততক্ষণ পর্যন্ত প্রত্যেকটা ম্যাক্সিমাম ইনপুট ভোল্টেজ চেঞ্জ হতে থাকবে। So if I go through the one example, suppose this is a 8 bit ADC, that means n is equal to 8, accepts an input voltage signal of range 0 to 10 volt. So 0 to 10 volt means the maximum voltage full scale is 10 volt. So 1 LSB will be the full scale voltage by 2 to the power of n. So that means we will get 1 LSB is equal to, that is called delta VI. So delta VI is nothing but a full scale voltage by 2 to the power of n. That means how many bits are there. So that is, from this example, we will get 1 LSB is equal to full scale voltage 10 volt by 2 to the power of n, that is the 39.1 millivolt. So now delta IFS for 1 LSB is equal to VFS minus 1 LSB. So VFS is 10 volt minus 39.1 millivolt, that is 9.961 volt from this formula. Then the digital output for an applied input voltage of 4.8 volt. 4.8 volt means is given by the digital. What is the digital output voltage of the input is 4.8 volt. অর্থাৎ যখন আমি ইনপুট ভোল্টেজ দেব 4.8 ভোল্ট, what will be the output voltage?
হ্যালো স্যার, এখানে 1 LSB বলতে সেটা বোঝানো হচ্ছে না, হাইটটা বোঝানো হচ্ছে না স্টেপের?
না, এটা 1 LSB means the depth of the stair. 1 LSB means depth of the stair. দেখো ভালো করে, this is the middle point input voltage. So then 1 LSB means 0.5 LSB left side, 0.5 LSB right side. So this is the depth of the steps. It's called the 1 LSB.
Okay.
Clear? So the IFS of the 1 LSB, that means the 9.961 volt. What is the minimum value of the input voltage required to generate a change of 1 LSB? আমাকে তো চেঞ্জ করতে হবে, প্রত্যেকটা ইনপুট একটা ইনপুট দিলাম, সেই ইনপুটটার করেসপন্ডিং বিট ভ্যালু আমাকে বের করতে হবে। Then one input, then the corresponding bit value. Like this, we will get the total output voltage bit by bit. This is the characteristics of the ADC. You will put the input voltage at the input of the ADC, you will get the corresponding digital value. So for one input analog signal, it should be considered as bit by bit. So first change, you will get 1 bit. Second change, you will get another bit. third change you will get another bit like this. So suppose this is an analog signal. How I will get bit by bit? If you will read it in analog communication and digital communication. ভুল করছি, এইভাবে গেল, এবারে এটা আসবে এরকম এরকম লাইক দিস, মানে এরকম ভাবে তুলে যাবে, আবার এরকম ভাবে তুলে যাবে, এরকম ভাবে আসবে। তো এটাকে যদি আমি এরকম ভাবে নামাই, so then you will get this value. At this input you will get 1, at this value you will get 1, at this value you will get 1. So bit by bit it will be changed. So this analog signal will be converted like this, as simple as this. Okay, so this is the depth of the stair. So this is the depth of the stair, 0.5, 0.5. Here this is 0.5, 0.5. Here this is 0.5, 0.5. Okay, so then you will get like this signal. Okay, so by quantization method in digital communication, you will learn in 5th semester, we will get this type of steps. Okay, there is some procedures are there. This is called the quantization. Okay, so by quantization you will get like these stairs. So before coming the analog and digital communication, you should learn only this. This is called the step size. This is called the step depth. Step depth is called the 1 LSB. It will middle portion is the analog input, and both 0.5 volt and the 0.5 volt is called the 1 LSB. So that is the 1 LSB means the depth of the steps. This is the depth of the steps. Okay. So come to the problem. What is the digital output of the input voltage 4.8 volt? That means the 4.8 volt is giving the input voltage by 1 LSB. This is the decimal value. So decimal value of D is equal to 4.8 by 1 LSB. We will already get the 1 LSB value. So that is the 4.8 by this. So this is the fractional value. Nearest decimal value is 1, 2, 3. Then this 1, 2, 3 treated as the binary. That will be the output voltage of the, that is the output voltage of the ADC. The 1, 2, 3 is converted to the binary. Then we will get this. So what is the procedure? First procedure is you should calculate the 1 LSB. When you will get the 1 LSB, then you should go for the decimal value of the input voltage. Input voltage by the 1 LSB, then that will be the decimal voltage. Then this decimal will be converted to the binary. So this is the 3 step. First calculate the 1 LSB. 1 LSB is nothing but a full scale value by 2 to the power of n, where n is the number of bits of the ADC. Then you will get the 1 LSB. When you will get the 1 LSB, then calculate the decimal value of the input voltage. Input voltage decimal value is calculated as the input voltage by the 1 LSB. Then you will get the decimal value. Then convert this decimal value to the binary value. Clear?
সেখানে অ্যাপ্রক্সিমেশন কেন নিচ্ছে স্যার? আমার পয়েন্টটাও তো ডেসিমাল ভ্যালুটা নিতে পারতাম।
গুড কোশ্চেন। তোমার অ্যানালগ কিন্তু কখনো ডেসিমাল হয় না, ফ্র্যাকশনাল হয় না, হয় কি?
ও আচ্ছা, না।
তুমি যখন একটা কন্টিনিউয়াস সিগন্যাল নেবে, this is the difference between continuous signal and the discrete signal. This is the continuous signal. Okay, so when suppose this is the time period, because continuous signal is with respect to the time t, and this is the amplitude a. Okay, So suppose this is a 1 millisecond, 2 millisecond, 3 millisecond, etc. So in between 0 and 1 millisecond, okay, so you cannot treat, this is the, suppose this is a 2 volt. So at 1 millisecond, you will get the 2 volt. But before the 0 to 1 millisecond, you cannot get any voltage. Okay? But,
Yes, sir, yes.
but in digital, if it is in discrete form, like this, like this, like this, suppose this is a 1 millisecond, 2 millisecond, 3 millisecond, 4 millisecond, 5 millisecond. What will be the voltage of 1 millisecond? 1 volt. 2 millisecond, 2 volt. 3 millisecond, suppose 5 volt. So then at certain point of time, you will get the certain voltage in digital. But in analog, you cannot say it. So what is the value of the 5 millisecond?
Yes, sir.
Okay. So this, for this reason, you should go for the integer part only, not fraction.
Okay, sir.
Now go for the another parameter that is called quantization error. যেটা আমি এতক্ষণ বললাম. That is the half LSB, that is called the 1 LSB. This is the step size, step depth. Clear? This is the step depth. This is the 1 LSB. This is the step here. Okay. This is the step. Like this. So what will be the value of the step? Depth. This is the 1 LSB. Now, if this depth of the step size is not similar or same for all the steps, then what happens? It should not be linear. তাই না? যদি আমার স্টেপ সাইজ সমান না হয়, তাহলে এই মিডল পোরশন গুলো কি সমান হবে? হবে না।
না স্যার, লিনিয়ার হবে না।
So we will not get any linear curve. So this is called the quantization error. So quantization error means if the half LSB is not same, then the depth of the steps will not be same. যদি এদিকে ধরো হাফ এলো না, এদিকে এলো 3/8, then the depth of the size will not be the same. So for this reason, the quantization error occurred. So quantization error value is plus minus half LSB. So if the maximum quantization error is the plus minus half LSB, কারণ এর থেকে বেশি হতে পারে না, এর থেকে কম হবে। এই সাইডে যদি হাফ হয়, এই সাইডে ধরো 3/8 পেলাম, so then the depth will be different. So for this reason, the quantization error is maximum is the half of delta by 2. Delta is the step depth, that is called 1 LSB. So 1 LSB by 2. So that means delta is the V maximum minus V minimum. This is the V maximum, this is the V minimum. So V maximum minus V minimum by 2. This is the number of levels. One level is 2 to the power of 1. If this is 2 level, then 2 to the power of 2. If 3 level, then 2 to the power of 3, like this. Right? So if there is an n number of bits, so then the maximum step size is
2 to the power n number of.
Exactly. So 0 to 7/8. So maximum quantization error is plus minus half LSB. So plus minus half LSB means 1/8 plus half LSB, 1/8 minus half LSB for first quantization error. For second quantization error, 2/8 plus half LSB minus half LSB. দিস ইজ ফর দ্য সেকেন্ড লেভেল অফ কোয়ান্টাইজেশন এরর। এরকম করে যতগুলো লেভেল থাকবে, দ্যাট মিনস n টু দি পাওয়ার অফ n, তো ততগুলো ইনটু কোয়ান্টাইজেশন এরর। তাহলে একটা বিটের জন্য কোয়ান্টাইজেশন এরর ইজ প্লাস মাইনাস হাফ এলএসবি। তাহলে n নাম্বার অফ বিটের জন্য কত হবে? n ইনটু প্লাস মাইনাস হাফ এলএসবি। সো আমি যদি এরকম একটা এক্সাম্পলে যাই,
স্যার হ্যালো স্যার,
স্যার
বলছিলাম নেক্সট ক্লাসের জন্য ডাকছেন স্যার।
নেক্সট হয়ে গেছে আমার, এটাই লাস্ট আর নেই। So quantization error is the analog voltage in the range of 0 to 8. So that means V mean is 0, V max is 8. So delta by 2 is equal to, delta is equal to step size, V max minus V mean by number of levels. এখানে লেভেল কটা আছে? 4 bit, so 2 to the power of n. So 8 by 16 মানে 0.5. So the quantization error will be, this is the one level. So half level কি হবে? Delta by 2.
Yes sir, yes
Plus
sir.
minus 0.5 by 2. So these are all are the quantization error. এই স্যাম্পলিং ফ্রিকোয়েন্সি এটা তোমরা এখন বুঝবে না, নন লিনিয়ারিটি তো আগেই বলে দিয়েছি। So that's all about the specifications of the ADC and the DAC. In the next class we will differently learn the different types of ADC and the DAC and their performances. Okay, construction and the performance, circuit design and the performance.
স্যার পিপি যেটা পাঠিয়ে দেবেন স্যার।
পাঠিয়ে দেবো।
স্যার
স্যার attendance
বলছিলাম, yes sir,
হ্যাঁ বলো।
স্যার অ্যাটেন্ডেন্স লিংক,
হ্যাঁ অ্যাটেন্ডেন্স